not against open access journals. I think it's wonderful to get science out to the people who need it everywhere. I'm all for it. But there is some issues with it. As you see, this was a fake cancer study, and a Harvard professor did this. He sent out 304 open access journals over 10 months, a paper that was totally bogus, just totally made up, bogus. 157 accepted the paper for publication, and PLOS One was the only journal that caught all the errors immediately and actually rejected it. 50% of the online journals rejected it without noting any of the major flaws. And it was the fact that the design of this study was so bad, was so wrong, that there's no way they could have come up with anything. So you wonder about peer review. You wonder about what did the people not have the skills? Did they just not do it because it was driven by money? I don't know. But there is a lot of literature that is not of high quality. On the other hand, there is a ton of terrific, very, very good literature that's out there in science. What you need to do in your career is to strive for doing the best science, being the best reviewer, having the best critiques, and never take anything for face value until you take it apart and until you study it and until you know that those results are, again, in terms of epidemiology, are as solid and accurate as they can be. There is no perfect study. Always know that. So we're going to spend time learning to critique papers. It's going to be a process, and that you'll get better at it. The more you do it, the better you get at it. During your career, you're going to have some mistakes. It's this, again, a great year in terms of trying to teach some concepts. Look at COVID-19. If you think of what we knew about COVID last year at this time, this was when it was just first starting to hear a little bit of rumblings about the nursing homes over on the West Coast. We didn't know anything. We had so little, yet people were making statements and saying, well, it's this or it's that, or this is good to do, this is not good to do, or it's associated with this and so forth. And then over the course of the year, you think where we are now, my goodness, we have a vaccine. We've gotten so much smarter. We've learned so much. So we made some mistakes a year ago. And you have to realize that in your career, you may make some mistakes with things you publish and that you do, or assumptions that you make. And as we get smarter and as we understand, like we do with COVID as an example, biology better, we get smarter, and so our interpretations also get better. So embrace these methods. Know you're going to have to go back over things. For the biggest examples I've seen of mistakes that have been in my career had to do with beta carotene. Back in the 80s and 90s, beta carotene was valued in over 125 case control studies. All these studies consistently said, oh, beta carotene is the way, the truth, and the light. It's going to be. It has protective effects, and it's great. We need to do that, and it's in fruits and vegetables. And so they said that it seems to work in racial groups, current smokers, former smokers, non-smokers. So wow, let's go do something. So the study started. Randomized intervention trials started in the 80s. The alpha tocopherol beta carotene study in Finland in 1985. 29,000 people were given 20 milligrams of beta carotene and 50 milligrams of alpha tocopherol. They had these wonderful, beautiful designs, well done studies. And you know what? When they got into the intervention studies, there was not one benefit to preventing lung cancer. Instead, there was a 16% increase in incidence of lung cancer, exactly what we'd hoped to prevent. And beta carotene group also had an 8% increase in overall mortality, and that was from heart disease. Well, it was worse because the CARROT trial was also being done with lung cancer, and they had 18,000 heavy smokers in that. And that study was actually terminated at 21 months early because after 4 years, the lung cancer incidence and total mortality in the group getting the intervention was increased. NIH shut down every study across the globe that was dealing with beta carotene. The research then had to go to all the patients who were been taking it and say, you may get lung cancer, and you may have a greater risk now. It was frightening. It was horrific what had to be done. I remember at one of the SER meetings, Society for Epidemiologic Research, the entire meeting was just focused on that. The rooms were packed. People were sitting on the floor listening to the investigators tell and talk about these studies and what it was like to have done this and what kind of mistake we made in science about this. So unfortunate things may happen. We'll get past them. You may too. But we can't ever go away from our understanding of epi basics, and causality is one of those fundamentals. Here we look for the criteria of necessary sufficiency, and we understand that there's caveats to that, particularly with observational research, because we can't do the true counterfactual, we can't do the true clinical trial sort of a thing, or expose somebody, not expose somebody, and see if they have an event. So we do observational studies. We look at risk measures. We look at relationships of factors and outcomes. So we have to be very critical, scrutinize everything. And then our goal with observational research is ultimately causality, and to try to get towards that down the path, since we can't totally prove it. And so we adjust for confounding as necessary, with the idea of that counterfactual sort of prediction. So the observational studies largely provide data for association, because we can't always have the temporality and we can't control all the design features. What we can do is plan our analyses in advance and do not deviate, change rules to just find a result. Don't fish. We set levels of significance. We make decision points a priority. What's going to be the number? What's going to be that level of difference that we are going to say makes a difference, that makes us decide that something is important? Some things that are being talked about now in the field are that perhaps everybody should always have a split data set. One is for modeling, and then one's your holdout. Once you finish, you keep this clean data set off to the side. Of course, it doesn't fit in every circumstance, but it's some of the things that are being discussed with how do we do this better, avoid any mistakes in the future. Well, that takes us to our first seminar. So I want to hop over to the seminar now and show you what we're going to be doing. First off, reminding of what we looked at the other day, which is, again, posted for you on Canvas, the information about seminars. And today you're getting the first paper. It is out there for you, and you get the first seminar guide. You will go through and read the paper, and you'll go through the guide. And as a part of that, you're going to very carefully critique this paper that you're given. Now, as I mentioned, that there's some articles on Canvas for you. We look here so you'll know where things are on the Canvas site. This is what you see on Canvas. If you see right here at the start of Canvas, you have all these basics about the labs and the homeworks and the seminars. And you have these three papers that I refer to here. One is the strobe guidelines, the other is the Prisma, and the other is Moose. And then how these are here to help you. If you look at any of these, and we'll take the first one here, which is the Moose. Why do I give this to you? This isn't the answers to your seminar. What this is designs, who the people are, who the variables are, biases, study size, quantitative variables. These are all the key elements. So the things that are here that I have given you in Canvas are resources to help you, and again, help your growth as an epidemiologist. The paper that you're actually getting today is this paper here, which is on sleep, obesity, and injury among career firefighters. This is one of our papers. This was done by a doctoral student who has graduated and working in the field and being very successful. I typically don't give a paper that I am an author on, but I went ahead and did this because it's such a nice example of confounding and effect measure modification. And there's still a lot of things to beat up about this paper. So I want to make it really clear right from the start, you are supposed to criticize this paper. You need to say things that are right and things that are not right about this paper. Remember, I'm the one who told you there is no perfect study. It's not perfect. These papers, these studies that we talk about, whether they're mine or somebody else's, they always have biases. They always have flaws. They always have things you could do better. And we always need to critique ourselves as well as our peers so that we can help to grow in our knowledge and help us in the future as we design studies and do things to set them up as well as possible. So you have this paper that's posted, and you also have this study guide. And this is the study guide. So you will go through, and this one is happens to be 44 points based on the questions that came up with for it. You have the reference, you have the paper, you have the directions of what you're to do. You're actually to take this Word file, and you are just to start typing your answers in here and just let it expand as you type answers to each of these questions. I want to be that this is not supposed to be an essay. These are meant to be short, brief answers. So as I said, keep things like 1 or 2 sentences. Typically, sometimes a word or a phrase or a list is fine if that's all you need. If you are supposed to write a sentence, we will tell you. It says, write one sentence interpretation. Well, then we expect a sentence that is readable and that makes good sense. Now, you're given 1 week to do each of these critiques so that you don't spend too much time on them, but you spend enough time. So that means you're not expected to read other published papers on the scientific content. You're not supposed to be an expert on sleep or obesity or anything like that when you're done. So don't go in hours reading a lot of other literature. As well, you will see in the questions, sometimes it says here here, like number 6, describe 2 examples from the description available in this paper of sampling bias. Now, if you wanted to go look up a lot of other papers that perhaps the authors had written, you might learn some other stuff. But I'm telling you, don't do that. I'm saying for this assignment, this is an academic exercise. 2 examples from what's available in this paper, all right, and how that could impact the sampling. That's what I want to know. So you have a lot of questions here. You expand them. To complete this, you turn it in by 10 o'clock by next Thursday when it's due, and we have the seminar in class, and we'll go over it all together. So I want to stop here and go back over here where I can see you guys better and see if you have any questions about the seminar before we leave this topic. Anybody? About what your expectations are? Nope. You're all good? All right. Wonderful. All right, well then we will leave this and go from here to our topic of the day, which is confounding. So this is a topic that you've had before. I know you have, and most of the topics you have in here, we have in this class, you will have had. You will have been over in another class. So or you may have had an entire semester on something, on some of the topics. And that's okay. What we do in here is the quick overview, the review. We hit the highlights of it, which means if you need to go do some reading on your own, then that's the expectation that you do it, because we need to move to what is the action statement, which is like next Tuesday when we go to lab. We're going to teach you how do you evaluate confounding, how do you do look for effect measure modification, and then how do you interpret it. So we go quick overview to then action with the actual doing part of the class. So start here with just a little background along those lines of resources and review. We have those articles in Canvas that I mentioned to you, particularly when we start to get into, I know the linear class, when we start to do a lot more interpretations. You're going to have some on your homework this time that you get next week, but we will be going back over and readdressing these issues about statistical significance and confidence intervals. So be sure, and p-values, of course. So be sure and read about that. So I'm going to start here today, and this is where we get to start having fun. I get to hear from you, and that is, how much do you remember about your EPI sort of principles and things? So you've got a nice 2-by table here, and we're going to talk about some of the measures that you're going to be doing in today and this whole semester about different risk measures. So first off here, if we look at risk differences and we look at risk ratios and odds ratios, using what's in this table, I need to hear somebody tell me how you calculate these things. So to get us started, Sarah, I'm going to ask you, what do you remember about how do you calculate a risk ratio?
The risk ratio is the risk of disease in the exposed divided by the risk of the disease in the unexposed. So I think looking at this, it would be A. So if you were to take the proportion of A over N1 and then divide that by C over N0, that would be your risk ratio.
Excellent. Good job. Yes.
Thank you.
So then, can you tell me what a risk difference is? And that risk difference, let's see, Natalia, can you tell me what a risk difference is, please?
Yeah, so that would be the same thing. Those with the disease that are exposed over the total exposed divided by those with the disease that are, minus.
Yeah.
Minus those with the disease that are unexposed over the total unexposed. So A over N1 minus C over N0.
All right. Wonderful. And Kenya, can you tell me how you would do a disease odds ratio?
I think so the odds of disease would be the odds of those that do have the disease among the exposed compared to the odds that those that don't have the disease among the unexposed.
And what would that formula be from here?
I think it would be, so in this table, it would be A over C divided by B over D, I think.
For a disease? Okay, Lauren, you want to help?
Yes. Is it A over B divided by B over or C over D?
Yes.
Instead of A over C, yeah.
Right. Now, mathematically, Tanya, what you said, we'd end up with the same stuff, right? But if we're looking at the true relationships, we need to specify correctly what we are doing, and that would be the actual formula for that. So the risk ratio was correct as stated here, the risk difference, and then this is the odds ratio for the disease. Okay? All right, good job. Now, what is the relationship between the odds ratio and the risk ratio? Rachel.
I'm not
Typically, what do we say? Okay, not sure?
Yeah.
That's fine. Zena, what would you say the relationship is between those two measures?
I could say maybe the odds ratio approximates the risk ratio when the prevalence is low.
Okay, when the prevalence is low. Do y'all agree with that? Y'all agree? Give me a thumbs up or not. You agree or not? I got a couple of thumbs. All right. Let's look at some of that. We will do that. So let's look at this. Now we've got some real numbers here. We've got a cohort with a rare outcome, and let's look at the risk ratio. So if everybody would take a sec here, pull out your phones, and calculate this with these little numbers that we have here. What is the risk ratio? We just went over what these formulas are. With some small, simple numbers here. We need a risk ratio, a risk difference, and the odds ratio. So if y'all would do those real quick, give you a minute. Okay, everybody got them pretty much? All right. So Olivia, tell me what you got for your risk ratio, please.
I got the value of 2.
Okay, you got 2.
As far as the interpretation, I'm still pretty certain.
Well, you don't have to interpret right now. You're all
Perfect. Good.
Not yet. We'll come back to you if you want to do it later. Risk difference. Tracy, what do you have? I'm not hearing you, Tracy. I think you're muted still.
Sorry, you wanted the risk difference?
Yes, please.
Oh, okay. I did the odds ratio, sorry.
Oh, all right. All right. So, Yuzi, do you have the risk difference?
Yes, can you hear me?
Yes.
0.02. 2%.
Okay. 0.02. All right, good. So, Tracy, let's go back to you. Let's get the odds ratio now.
I have 33.4, something like that. Sorry, I'm slow.
Well, I'm not sure how you got that.
I don't know.
Okay.
Yeah, I'm slow.
Okay, that's all right. That's all right. So, Susan, what did you get for the odds ratio, please?
2.
Okay, 2 or 2.04, something close to that. So if we look at, these numbers now and we see what we have here, we have these 3 numbers that we talked about. And again, we're still going with this idea of what's the relationship here between our risk ratio and our odds ratio with trying to understand that better. Here you see when we have a rare outcome, we have a risk ratio that results in here at 2, and the odds is 2.04. So these are really quite close. Well, let's look at it with this data. Again, another close cohort with a common outcome. And let's calculate these three real quickly. So pull your phones out again and do these, please. Tracy, could you mute, please?
Sorry, what?
Could you mute, please?
Yes, I'm sorry.
That's fine, thanks. So to get started with these, Justin, I'd like to see if you guys can speak from Houston, if possible. If not, just wave your hand. I understand. Is it functioning so that you could to give us what the risk ratio is, please? Just wave your hand if you can't, or something. See, y'all can't talk. Okay. Oh, that's too bad. All right, so we will skip our folks in Houston. Let's see, Napur, what would you get for the risk ratio?
1.02.
Okay, 1.02, good. And then for the risk difference, Matthew, what do you have? Do I have Matthew? Yeah. Matthew, if you're speaking, we don't hear you. Maybe he's in Houston. I don't think so. All right. Susan, can you give us what the risk difference is?
It's 0.02.
Okay. And then the odds ratio. Tahini?
It's 2.04.
Okay, good, good. So if we take these and we look at these results, we have the risk ratio, the risk difference, and the odds. And now we're having these data results from what would be a common outcome. And we look at what this relationship is here between the risk ratio and the odds. These start to be much more different as it becomes a more common outcome. So these are the kinds of principles to understand as we begin to evaluate and look at data, and going back to just basic calculations. We do some of these basic simple calculations as a part of class to show and help you remember concepts of how, as one thing goes up, one thing changes, the impact that it could have on risk estimates. So that when you get into larger data sets and into interpretive sorts of situations, and you have common outcomes or non-common outcomes, rare things,